Thank you for the introduction, Dr. Kai. So my summer project has been focused on the combination of MDM2 inhibitors and Mech inhibitors as a therapeutic strategy for NRAS mutant melanomas. So what is NRAS? NRAS is a member of the RAS protein superfamily. And these proteins are very important because they are notable oncogenes, meaning that if mutated, they are very likely to cause cancer. So if we break down melanoma cases, we can see that 50% of melanomas have a BRAF mutation, while 30% of melanomas have an NRAS mutation. Making up the majority of cases, BRAF mutations have had ample research done on them and have had targeted therapies developed for them. On the other hand, there are no targeted therapies for NRAS mutant melanomas, and metastatic patients have to first go through immune therapies and then chemotherapies as a form of second-line treatment. While 30% is the minority of cases, it is still a significant amount, and so the goal of our project is to develop a targeted therapy for NRAS mutant melanomas. So one of the drugs we work with here are Mech inhibitors, and what these do are that they slow cell growth and proliferation in the body. This process starts with growth factors and their receptors in the body. So the growth factor interacts with the receptor, and it triggers a series of protein interactions that eventually leads to cell growth and division. And so what Mech inhibitors do is that they target this protein here called Mech. And if we can halt the activity of Mech, we can slow down everything that happens downstream of Mech. So Mech doesn't get to interact with ERK, and then ERK can't go on to cause cell growth and division. An important note are that Mech inhibitors are approved by the FDA, but they do not have strong efficacy against melanoma when used alone. Another drug we work with are MDM2 inhibitors. And what these do is that they allow the accumulation of p53 and increased tumor suppression. So p53 is a very important protein in the body when it comes to tumor suppression and cancer prevention. What MDM2 does is that it interacts with this protein called MARCH7. It then goes on to add these ubiquitin groups onto p53, and what these ubiquitin groups are that they essentially target p53 for destruction, and then the cell will degrade p53. So again, if we can slow down the activity of MDM2, we can slow down the destruction of p53 and then increase those tumor suppressive qualities. Additionally, 19% of melanoma patients have what's called a TP53 mutation. This means they have an abnormal form of p53, but in our project we focus on the 80% of melanoma patients that have a wild-type p53 because they are more responsive to MDM2 inhibitors. Like Mech inhibitors, MDM2 inhibitors are approved by the FDA, but they do not show strong efficacy against melanoma when used on their own, which is why we look to combine them with Mech inhibitors. Lastly, gasdermin E is a protein in our body that triggers a type of inflammatory cell death called pyroptosis. So what happens is that the chemo drugs interact with the cancer cells and they cause activation of gasdermin E. Then this enzyme called caspase-3 comes in and cleaves gasdermin E into its active form. This active form of gasdermin E interacts with the cell membrane and essentially opens holes in the membrane. Out of these holes, the cell contents can leak out and it eventually causes the death of the cell. This type of cell death is called pyroptosis, and in addition to killing cancer cells, it has additional anti-cancer benefits, including tumor shrinkage and regression, a decrease in metastasis, and most importantly, our increased recruitment of immune cells. So not only does it kill cancer cells, but it also strengthens our body's natural immune response for cancer. In this experiment, we look at two cell lines, SBCL2 and WM1361A. We then split the cells into 4 groups. One is the control that receives no treatment. The second group receives mabtamatlin, which is an MDM2 inhibitor. The third group receives trametinib, which is a Mech inhibitor. And then the fourth group receives the combined treatment of both drugs. After treatment, we can observe varied levels of cell death among the 4 groups. And then using Western blot, we can monitor the activity of gasdermin E among the 4 groups. And with a cell death assay, we can determine the synergy of the 2 drugs. And so the goals of our experiment are to, 1, determine if these 2 inhibitors can work together to cause more cell death than they would alone, and then 2, to determine if this cell death is associated with increased activation of gasdermin E. So our hypothesis is that the combined application of MDM2 inhibitors and Mech inhibitors induces a synergistic cell death through increased gasdermin E cleavage, leading to pyroptotic cell death. So here are our Western blots results for the SBCL2 cells. We have a number of controls going on here. We use vinculin as a loading control, P53 as an MDM2 inhibitor control, and then phosphorylated ERK as a Mech inhibitor control. And the important thing to note here is the activity of gasdermin E. So these 2 bands here represent that cleaved active portion of gasdermin E, and we can see that the cells treated with trametinib, as well as the combined treatment cells, saw an increased activation of gasdermin E. We can also look at the caspase-3 levels. That's that enzyme that cleaves gasdermin E. And we didn't see a strong signal for any of the 4 groups, but this could be attributed to other caspases that can also act to cleave gasdermin E. Then for the WM1361A cells, we have the same controls going on. Important to note that all cells treated with drugs saw an increased level of gasdermin E. And we can see that since this band here is darker for the combined treatment, it shows a slightly increased level of gasdermin E activation in the combined treated cells. Again, we look at the caspase-3 levels, and we can see that the combined treatment cells saw the highest caspase-3 levels of the 4 groups. With the cell death assay, we can analyze a group of cells and see which ones are going through cell death. So each dot on these graphs is a cell. And what we want to focus here is this number in the top right quadrant, and that'll show us how many cells are going through pyroptosis. So we can see with the SBCL2 cells, most of the control cells were healthy, and we saw a slightly increased amount of pyroptotic cell death in both the nab-to-madlin and trametinib treated cells. Both of them had around 10%. And then in the combined treatment cells, we saw that 22% of cells were going through pyroptotic cell death. We saw a similar phenomenon for the WM1361A cells, mostly healthy cells in the control group. Nab-to-madlin and trametinib saw an increased amount of cell death with 47% and 17% respectively. And then we saw a very large increase in pyroptotic cell death here with the combined treatment, having 73%, a majority of cells going through pyroptosis. So what conclusions can we draw from our experiment? Both nab-to-madlin and trametinib cause melanoma cell death on their own. However, when combined, they're able to synergize and cause an increased amount of cell death. The combined application of these 2 inhibitors is also correlated with that synergistic activation of gasdermin E. Future directions. What can we do from here? So one of the first steps we want to take is to look at the release of inflammatory cytokines. We know that gasdermin E pyroptosis is an inflammatory cell death, so if we harvest the supernatant of the cell culture, we can monitor the release of that of inflammatory cytokines. And then we can see if gasdermin E mediates that release of inflammatory cytokines by knocking out expression of the cell, seeing if that release of inflammatory cytokines goes down, and then restoring expression and seeing if it comes back. And then, as with all these presentations, the end goal is application in the medical field. So we'd want to do some animal work to investigate the efficacy of the combination of these 2 inhibitors in a live model. So I'd just like to give special thanks to everyone who helped me and taught me and was patient with me this summer. Of course, special thanks to the Simmons Cancer Institute, and then all of you guys who came out here in support of us today. Thank you.
Questions? Yes.
So how long will it take from the experiment stage you're in to get to the mainstream treatment for patients?
Well, I'm not very well versed in that, but I'd say a pretty long time. I mean, you first have to have good enough results to be approved for animal work, and then after that, have good enough results to be approved for clinical trials, then good enough results to be used in patients. So it's a long process, I'd say.
So just to get an idea, from animal models, you go to a phase 1 trial, and phase 1, you're trying to determine the toxicity of the drug in human models, in human volunteers. And from phase 1, you go to phase 2, where you're trying to determine the efficacy of the drug. And then you have to go to phase 3 trials, where you compare your new combination to the standard of care. Each of these studies can take anywhere from 3 to 7 years, unfortunately. Yes?
As a supplemental, these two drugs are approved by FDA, so the clinical toxicity is minimal. However, the combination of these two drugs, we don't know if it can cause further toxicity in the patient, so we still need to clinical trial 1, trial 2, 3. Okay.
It looks like pretty significant result, So when is the publication coming up? When are after the animal?
Yes, we have one more question, please.
I'm just curious, when you worked with the two together, were they in equal portions, or did you try varying combinations of more of this or more of that?
We tried varying combinations.
To try to find the
best, ratio of the two. Yeah.
Okay, thank you.
Thank you.